Hi everybody, Amanda Pilz here with Chemistry 125, here to do lab number 7. Today we will be explaining and demonstrating different molecular geometries using balloons. These balloons will represent electron pairs, both bonding and non-bonding, and their arrangements will show the shapes molecules take based on how many bonding areas and lone pairs are around the central atom. For my first example, I'm going to demonstrate linear molecular geometry, which occurs when there are two bonding areas and no lone pairs. A common example is carbon dioxide, CO2. I'll use two balloons for this demonstration. The two bonding areas form a straight line, so looks a little something like this, with a bond area, a bond angle of 180 degrees. So that's a half circle right there. This creates the linear shape. In this case, the electron domain geometry is linear because there are only two regions of the electron density. The molecular geometry is also linear. The second example, I will demonstrate a trigonal planar geometry, which occurs when there are three bonding areas and no lone pairs. A good example is boron trifluoride. We'll use three balloons for this demonstration. The balloons naturally spread apart to form a flat triangle, which is why it's called planar, and the bond angles are 120 degrees. For this molecule, the electron domain geometry is trigonal planar, and the molecular geometry is also trigonal planar because there are no lone pairs. Now I'll show you a bent molecular geometry with one lone pair. This happens when there are three electron pairs around the central atom, but one is a lone pair. A good example is sulfur dioxide, or SO2. Here we'll use three balloons again, two for the bonding areas and one for the lone pair. The lone pair pushes the bonding pairs closer together and gives us this bent shape, with bond angles that are slightly less than 120 degrees. In this case, the electron domain geometry is trigonal planar. The molecular geometry is bent due to the lone pair. Next, let's take a look at tetrahedral geometry, which occurs when there are four bonding areas and no lone pairs. An example is methane, or CH4. For this demonstration, we'll use four balloons. These balloons spread out to form a tetrahedral shape here with bond angles of 109.5 degrees. For this molecule, the electron domain geometry is tetrahedral, and the molecular geometry is tetrahedral because there are no lone pairs. Next, let's take a look at the trigonal pyramidal geometry, which has three bonding areas and one lone pair. A good example of this is NH3, which is ammonia. I'll use four balloons here, with the top one representing the lone pair. The lone pair pushes the bonding areas down, forming this trigonal pyramidal shape, kind of like this. This is what it looks like from the bottom. The bond angles are slightly less than 109.5 due to the repulsion of the lone pair. The electron domain geometry is tetrahedral, and the molecular geometry is trigonal pyramidal. Now let's look at bent or angular with two lone pairs. A good example of this is H2O, where the oxygen atom has two bonding areas and two lone pairs, and this results in a bent or angular geometry. So we'll use four balloons for this one, two representing the bonding areas and one kind of in the back, one kind of in the front for the lone pairs. The lone pairs push the bonding areas even closer, and that creates this kind of bent shape with bond angles of around 105 degrees. For this molecule, the electron domain geometry is tetrahedral, and the molecular geometry is bent. Next, we have the trigonal bipyramidal geometry, which occurs when there are 5 bonding areas and no lone pairs. An example of this is phosphorus pentachloride, or PCl5. For this, we'll use 5 balloons. So we have on the bottom here that pyramid shape, and then kind of one in the front, one in this back a little bit. 3 balloons form this flat triangle with bond angles of 120 degrees, while the other form 90-degree angles with the plane, creating a trigonal bipyramidal shape. Next, let's look at the T-shaped geometry, which occurs when there are 3 bonding areas and 2 lone pairs. A good example of this is chlorine trifluoride, or ClF3. For this, we'll use 5 balloons again, so we have this and kind of one in the back here. 3 of these balloons are to represent the bonding areas and 2 for the lone pairs. The 2 lone pairs will push the 3 bonding areas into a T shape with bond angles about 90 degrees. And the electron domain geometry for this is trigonal bipyramidal, and the molecular geometry is T-shaped due to the 2 lone pairs. Next, we will look at another linear geometry, but this time it's with 3 lone pairs and 2 bonding areas. A molecule that is an example of this is xenon difluoride, or XeF2. So for this one, we're going to use 5 balloons again, and we've got 3 in the front here and kind of 2 sort of in the back. And if you'll notice, this bond right here, just like the first linear shape we showed, is 180 degrees. 2 for the bonding areas on the balloons and 3 for the lone pairs. The 3 lone pairs arrange themselves to minimize repulsion, which leaves the 2 bonding areas directly opposite of each other to form the linear shape with the bond of 180. In this case, the electron domain geometry is trigonal bipyramidal, and the molecular geometry is linear because of those 3 lone pairs. Next, I'll demonstrate the octahedral geometry, which occurs when there are 6 bonding areas and no lone pairs. A good example of this is sulfur hexafluoride, or SF6. For this demonstration, we will use 6 balloons. And so I've got 4 in the front here, and then these 2 are in the back. The 6 bonding areas naturally arrange themselves to be as far apart as possible, creating that octahedral shape with bond angles of 90 degrees in between all the bonds. The electron domain geometry is octahedral, and the molecular geometry is also octahedral because there are no lone pairs. Now let's look at the square pyramidal geometry, which occurs when there are 5 bonding areas and 1 lone pair. An example of this is bromine pentafluoride, or BRF5. For this demonstration, we'll use 6 balloons, 5 for the bonding area and 1 for the lone pair. So we've got 4 in the front and 2 in the upper back right there. The lone pair pushes the bonding area slightly, distorting the octahedral structure into the square pyramidal shape with bond angles slightly less than 90 degrees. Lastly, we have the square planar geometry, which occurs when there are 4 bonding areas and 2 lone pairs. For this demonstration, we'll use 6 balloons. We've got the 4 kind of up front and the 2 in the back, angle like that.